Here's the solutions to Chapter 13 homework. Which deals with pressure, fluids, things like that. I was a bit concerned, to be honest with you, that some people did a decent job, but there's a lot of people who just kind of did well, I got stuck, or I didn't know how to do this. And you haven't come in for extra help, and I don't think, um, were able to use your AP Physics to 5 steps to a five or the book information to make a lot of progress. So these are things you're going to have to put in thought, and you're going to have to not do last minute and use those other resources, be it me, 5 steps to a five, others, classmates, things like that. So again, I really encourage that you do that. For P5, we didn't go over that, but basically, if you end up having a radius half, the volume of the sphere is reduced by a factor of 8, so therefore your density would increase by a factor of 8. So it's 11.2 kilograms per cubic meter. For problem 8, I almost made the same mistake as the book did, and that for some reason I thought the surface area of a sphere is 4/3 pi r cubed. It is not. It is 4 pi r squared. So I believe we did this one in class on Monday, December 9th, and I ended up getting like 422 million newtons was the force on that small sphere, but it was at a huge depth, 11,000 meters. For problem 13, it's asking about the maximum depth of a submarine, and it said that the pressure inside we assumed was 1 atmosphere, so we're only worried about the extra pressure caused by the depth. So if we're thinking salt water, which makes sense, it's 1,030 kilograms per cubic meter, and we're looking to find that the maximum force on a window is 1 million newtons. Well, we'll find the area of the window by pi r squared, and then take that force divided by area. That gives us our pressure, which is 3.2 times 10 to the 7th, or 32 million pascals, and that equals rho GD. So that equals the maximum depth we could be, which is about 3,150 meters. For problem 14, what's the mouth? That's weird. I gotta go look at that. I did not remember that particular question. So for problem 14, um, number, let's see here. Okay, this was the highest. Someone can pull up water due to atmospheric pressure. So the atmosphere is 101,000 pascals. You're trying to find the minimum pressure in the person's mouth so that they can pull it up 2 meters. And so basically the pressure in the mouth plus that 2 meters of liquid equal the atmospheric pressure. So it says that you can reduce the pressure inside your mouth when you're inhaling to around 81,700 pascals. 19 we did in class, but I think that was one of the tougher problems. So note that I've got a color-coded solution here. Purple means mercury, green means water. Must be some algae growth, who knows? So for whatever reason, the problem said that the water was added on the left side, and I did on the right side here. Don't get confused by that, obviously. So in this particular case, remember the reason that we're subtracting this is that the height of the mercury decreases on the right side, it increases on the left side. So that will result in equal pressure on each side. And I noted that over here. So for problem 21, it was asking about a cargo barge loaded in salt water and asking how deep it would sit in the river. Well, if fresh water is less dense than salt water, then to push aside the same mass of the boat, you would need to end up being deeper. So in my mind, it should be at least a little bit deeper. Fresh water is 1,000 kilograms per cubic meter. Salt water is, or seawater is 1,030 kilograms per cubic meter. So I multiply length times width times depth, which got me the volume of the salt water that was displaced, multiplied by the volume by the density. That tells me the mass of the salt water that's displaced. So that's the mass of the barge. So in fresh water with less density, I go and I see that I'm going to end up with more volume displaced to support the same mass. So I can go back and use that volume as length times width times depth. The length and width are fixed, but the depth increases to about 0.824 meters. So that is something that ships that undergo going from saltwater to freshwater do have to think about. It's not a huge amount, but again, that's 3%. Okay, for problem 23, it's fantastic. It's talking about a wood block with a density of 700 kilograms per cubic meter, or 0.7 grams per cubic centimeter. And it floats in waters. It says what's the distance to the top of the block, if it's fresh, or if it's seawater. If it's fresh water, again, the density is 1,000 kilograms per cubic meter. So 7 centimeters is in fresh water, so 3.0 centimeters would be above the water. In salt water, which is more dense, it's going to float higher because you don't have to push aside as much volume of water to push aside the same mass. How much mass were we pushing aside? Well, it was 700 grams, or 0.7 kilograms. So here in salt water, that length times width times depth times density to equal 700 grams means that we would end up having 6.8 centimeters in the seawater, so 3.2 centimeters above. For problem 24, I was trying to work that out in class. I did kind of a crappy job of it. So the key thing is in order to haul a payload, you need to have a net buoyant force up, and air is 1.2 kilograms per cubic meter, helium's about 1/6 of that, 1.166 kilograms per cubic meter. So the buoyant force is essentially the density of the air times V times G. So that's 67,032 newtons, or 6,840 kilograms of mass equivalent. But the mass of the helium isn't zero, it's 946 kilograms, because it has a density as well. And so the gondola has the mass of 4,300 kilograms. So we've got this amount of mass that could be lifted minus the mass of the gondola minus the mass of the helium. So we end up with a net payload of 1,594 kilograms, or 1,600 kilograms, or around 16,000 newtons. So I think I was trying to do this method in class where you could find the net lifting ability by taking the difference between, that should not say difference between the masses, that should say the difference between the densities. I will fix that. And I will fix that. 10. Just make the writing green so that it'll look good. Put white in the gray in the background. Gray in that. Yeah, it's okay. Difference in densities multiplying by volume and G. Nice try, Forrest. 25 is actually a really good problem. So hopefully that you're doing things like this a bit in your density lab. So you've got an aluminum block sitting in ethyl alcohol, so that density is not water. It's asking the tension of the string. So I want to think about a free body diagram. I'm going to find the weight of the aluminum. That's the density of the aluminum times its volume times G. So it said it was 100 cubic centimeters, but there's 1,000,000 cubic centimeters in 1 cubic meter. So make sure you know how to do those conversions. And you just didn't put 1 to 100. That's meters to centimeters, not meters cubed to centimeters cubed. Anyhow, that's 1/10,000th of a cubic meter. And so that ends up being that the weight of the aluminum is 2.646 newtons. The buoyant force is equal to the density of the alcohol multiplied by the volume that's displaced multiplied by G. So that's 0.774 newtons. So the tension is going to be the difference between those, and that's 1.87 newtons. Like I said, I think I'd look over this problem. That is a really nice one to think about. Problem 35 says a 1 centimeter diameter pipe widens to 2 centimeters and then narrows to 0.5 centimeters. So you're basically asked to find the speed and the volume flow rate. Well, the volume flow rate is area times velocity. So I do pi r squared times the initial velocity, which is 4 meters per second, and I get pi times 10 to the negative 4th cubic meters per second. To find the speed, I need to think about the fact that if the pipe widens or doubles in diameter, its area is going to be 4 times as much. If the pipe gets half as wide, its area is going to be 1/4 as much. So in the first segment, with the area being 1/4 as much, the speed would actually have to be 4 times, or pardon me, with the area being 4 times as much, the speed would have to be 1/4 as much. So that'd be 1 meter per second. The second part, where it narrows down, the speed would have to be 4 times as much because the area is 1/4 as much, and it's 16 meters per second. For problem 37, that is an example of a small pipe that's changing diameter, changing height, changing speed, changing cross-sectional area. So this is a Bernoulli equation problem. Seems really long, but again, you're given a lot of information, like that the absolute pressure is 200,000 pascals here, and that it goes up 10 meters, and the speed here is 2, and the speed here is 3. So I think the key thing with that is just make sure you don't get confused with things. This is really an energy equation. It takes work to lift that liquid up there and to get it going a higher speed. So that's what causes the pressures to be different. A lot of times what they'll do is they give you a cross-sectional area up here and down here, and then you'd have to figure out the speed up here, and then you can figure out the other things as well. But in this case, they pretty much gave you all the information, density, height, speed, stuff like that. So the pressure up here is going to be less. It's around 110,000 pascals. Hopefully that makes sense. Where you have high pressure, you're going slow. Low pressure, you're going fast. Why? Because that pressure is what speeds it up in between the slow and the fast areas. Problem 45, I misassigned. I will not do that again. Problem 65. It's the last one. And we've got a liquid up here. We've got liquid flowing down here. It comes up here. It's flowing out at 4 meters per second. It tells you the area down here or up here and down here. So the key thing is what's the pressure exiting? Well, that's atmospheric pressure, which they're going to call 101,300 pascals. AP calls it 100,000 pascals. For letter B, it says find the height of the column of water. We need to find the pressure at the bottom point. So basically we're trying to find the height of this thing. So we need to find the pressure here. So we know this is atmospheric pressure, and we know that this is a certain area. So the first thing we got to do is figure out how fast we're going down here. Well, if I know this is double the area, it's going to be going half as fast. So that's going to be 2 centimeters per second, or 2 meters per second, pardon me. And that's written in purple. Although the area units are non-standard units, it is proportional. So again, A times V equals A times V. 5 units of area times 4 meters per second is 10 units of area times 2 meters per second. So once I get that, really what I need to do is I need to find the pressure down here. Well, using Bernoulli's equation again, this whole thing is 0 because we're at the bottom. 1/2 rho V1 squared, we just figured out that V. P2 at the top, that's atmospheric pressure. This is the additional factor that would be caused by it being raised or elevated. That's rho GH. This is the additional factor caused by it moving, 1/2 rho V squared. So again, this relates to gravitational potential energy. This relates to kinetic energy. So all those three things on the right side add up to a certain amount. On the left side, the only non-zero factor you have is based on how fast the liquid's moving down here, which is 2,000 pascals is what's caused by that. So when I solve for P1, I get 146,500 pascals. So to support the water column at H, the pressure would equal atmospheric pressure plus rho GD. So I know that I've got 146,500 pascals down here. I know atmospheric pressure is 101,300. So that's plus rho GD is the pressure caused by the liquid. So that liquid depth is 4.61 meters. So essentially what that means is this water up here is higher than this, which might seem a little different compared to what we've talked about with pressure being equal at all at any given height. But that's because it's moving slower here than here. That's why it's able to push it up higher than this. So hopefully that makes sense why this open pipe is 0.61 meters essentially above where this water is flowing right here. And that's it.